Hi everyone. In this video, we will learn about bond polarity and types of allotropic forms of carbon atom. But before we get there, let's talk about properties of ionic compounds. We've learned about ionic compounds formed between metals and nonmetals. Ionic compounds are hard, brittle solids, and they have different colors because of the color of the metal. Let's talk about the properties of ionic compounds. They're very strong bonds, high energy. It's not easy to break that ionic bond. They have high melting and boiling points. They're very hard, brittle crystals, as I just showed you before. As I said, various colors because of the metal ions. As we talked about electronegativity, that the difference between the electronegativity has to be more than 0.7, 1.7. As I said, some books say 1.7 or 1.8. Some books even say 2.1. So greater than 2.1 or 1.7 is ionic, means that the other element has enough power to pull the electrons completely over. So it's not being shared anymore. They don't conduct electricity in solid state. So a lot of you get mistaken here, that you just remember that ionic compounds are good conductors. But you have to keep the difference in mind, that ionic compounds are good conductor in solution when they're dissolved in water, not in the solid state. So they do not conduct electricity in solid state. In aqueous solutions, they do, and they're called good electrolytes. So keep these things in mind. The next thing we want to talk about are the metallic bonds. Metallic bonds are not like ionic bonds or covalent bonds. They're not formed by the transfer of electrons or sharing of electrons. These are the bonds between the metals, and they are actually the metal atoms. These are all metal atoms. They're holding each other because of the delocalized electrons. They're valence electrons. So usually this happens in the d block elements. As we know that the d block elements have a lot of electrons in the d sublevel, and those d sublevel electrons can move freely. So they jump up to 4s, then they jump back to 3d. So they're called delocalized electrons, and because of these delocalized electrons, like if it is the valence electrons of iron, then they will not just stay around this iron. These electrons will move down to this iron, or these electrons will then slip into the other iron. So we call them delocalized. So since they're continuously slipping around, they can conduct electricity. So whenever anything needs to conduct electricity, it needs those free moving electrons, okay, or we call them delocalized electrons. We also call it the sea of electrons. So it is that sea of electrons that makes metallic bonds very good conductors, and they have also very high melting and boiling points. So I'm talking about metallic bonds that are formed between metals. And when we say between metals, we are usually talking about these metals. That's where we get the alloys, the metals of different mixtures. That's why, one metal, for example, copper, is very soft because metal itself is very soft. So to make it harder, we can add other elements in it. And that makes it harder because those electrons are held by more than one nuclei. So that makes them harder than being soft, being an individual metal. So properties of metallic bonds, as I said, they're very strong, high boiling points, high melting points. They're good conductors even in solid state because of those delocalized electrons. They're malleable, means you can slice them into sheets. Ductile, you can turn them into wires, and they're shiny. Covalent compounds, we learned earlier on, they're formed by the sharing of electrons, not by the transfer of electrons. Okay, so the next thing we want to talk about is bond polarity. I know that we talked about geometrical shapes in last class. Right now, what I want to talk about is bond polarity. We talked about linear molecules. We talked about trigonal planar, tetrahedral, trigonal pyramidal, and we talked about bent. Okay, We also talked about electronegativity. So by electronegativity, you can discuss the bond polarity. For example, the bond between nitrogen and hydrogen. The bond is going to be polar because electronegativity of nitrogen is much more than the electronegativity of hydrogen. So the bond is polar. But uh, today we will talk about the molecular polarity. So these are two different terms. Okay. I know that we did learn this in previous chemistry class last year. Whenever you took the chemistry before, you have talked about bond polarity and molecular polarity. So let's talk about bond polarity in terms of carbon dioxide. So carbon dioxide, the bond is polar, oxygen is partial negative, and carbon is partial positive because of the electronegativity difference. So I will say that the bond is polar. But when we have to calculate molecular polarity, uh, in general, when you learned the chemistry last time, you were told that the pull on this side is balanced by the pull on this side. But at your level, at the IB level, they're talking about the parallelogram method, where you have to add the vectors. You have v1 and you have v2. So to get the v net, the net, you have to add two vectors together. Okay, so then that decides what is going to be the molecular polarity. So let's say I have a vector in this direction because bond is being pulled, electrons are pulled in this direction. But then I have assumed that the bond polarity here is 0.8. Okay, so if I have 0.8 strength on this side, then I have the other vector of 0.8 because it is the same molecule in the opposite direction because negative end is on this side. So since two vectors, the v1 and v2, the two vectors are of the same value, okay, and they are in opposite direction, they cancel each other. On the other hand, if I have HCN, this is also linear, okay. HCN is linear, and if I want to talk about their bond polarity, we know that hydrogen is less electronegative than carbon, which is less electronegative than nitrogen. Okay, so the bond is going to be polar in that case. But this is how the polarity is going to be. This is going to be partial positive. Compared to this is partial negative. But then if you talk about this bond, carbon is going to be partial positive, and this is going to be partial negative. So I have one vector of certain value. I can get the electronegativity difference. I have one vector of some value being pulled on this side. Then I have another vector, okay, of a different value, which is also pulled in this side. So in this case, the net vector is being pulled in this direction. Okay, so I have to add the two vectors to calculate the molecular polarity, so they don't cancel each other, but actually they're creating a polarity in the molecule. So this molecule, although it is linear, but it is asymmetrical also in shape. Okay, so it is going to be polar. Okay, so the bond is polar, bond polarity is yes, and the molecular polarity is also yes. Okay, like for here the bond polarity was yes, but the molecular polarity was non-polar, because they canceled each other. Here the bond polarity is polar, so as the molecular polarity, because they were both in the same direction. So bottom line is, if you have a symmetrical shape, the bond could be non-polar. Like if I have CCl3, the bond is going to be polar. Okay, chlorine is partial negative, this is partial positive. So the bond is polar, but the molecule is going to be non-polar because of the shape, the symmetrical shape. Okay, now which shapes are symmetrical shapes? The symmetrical shapes are the ones that cancel each other. Their vectors will cancel each other. So that is tetrahedral, okay, tetrahedral, and trigonal planar, and linear. There are always symmetrical, So even if the bonds are polar, the molecules will be non-polar. But there is, you have to keep in mind that, as I said, that if the bonds are polar in CCl3, even if the bonds are polar, the molecules are non-polar because they cancel each other. But if I have CHCl3, the elements are different on the other end. Like this pole is cancelled, this vector is cancelled by this one, but this value, the pull, the value of v1 is not going to be the same and in opposite direction, so this is because this is partial negative, this is partial positive. So instead of going in the other direction, it actually goes in the same direction. So this makes the bond polar. Okay. uh, so this is, non-polar, this is non-polar, but this one makes it polar. All right, so if the elements on the ends are different, then even if the bonds are polar, the molecule will also be polar. So for the molecule to be non-polar, the elements have to be same. They all have to be same. If I change one, it will make the molecule polar. So as I said, even linear, it is symmetrical, but the elements have to be same on both ends so that they can cancel each other. If the elements are different, okay, that will make the molecule polar again, even if it is linear. Now, which shapes are asymmetrical? Asymmetrical shapes are bent and trigonal pyramidal. They are always polar. Okay, these are always polar. Even if their bonds are non-polar, the molecule is going to be polar because of the free electrons. The the delocalized electrons. They take more space on the central atom. They kind of bend the bonded pairs downward, and that makes the element to be polar. It makes the molecule to be polar. So asymmetrical shapes, which is bent and trigonal, pyramidal, always polar, and symmetrical shapes, which are tetrahedral, trigonal, planar, and linear, are always non-polar. So this is the molecular polarity. I want you to read page number 115. Okay, as a matter of fact, you should be doing all the examples. Starting page number 111 all the way through 115, which talks about molecular polarity. I want you to study those study tips, read all the details. You should be able to deduce the molecular polarity by adding the vectors. You should be able to calculate the molecular polarity, by giving the electronegativity values. So this is all going to be on your quizzes or tests, how to calculate bond polarity and how to deduce the geometrical shape and molecular polarity. So, but if you have any questions, we will discuss it in class. Well, the next thing, uh, anyway, here is a summary again. The type of bonds, non-polar bonds, they're always non-polar, if they are between similar atoms, Cl2, Br2, because the difference is zero, so they're always non-polar. But if the bonds are polar, then it depends on the symmetrical shapes. Even if the bond is polar, the molecule will be non-polar. Uh, if the bond is polar, the molecule will also be polar if it is a asymmetrical shape. So it is kind of a summary that I had talked about before. But the other very different topic we want to talk about is carbon. We have discussed in chemistry many times that carbon is a very unique element. And what makes carbon so unique? Why we have the whole chemistry of carbon, which is called organic chemistry. That's the chemistry of carbon-based compounds. One reason is that this is the life is based on this. Most of the living organisms, their compounds are made of carbon compounds. But the other thing is that carbon has a very unique ability that no other element has. And that is because carbon can make single bonds, carbon can make double bonds, and carbon has the ability to make triple bonds. So this uniqueness is only it only belongs to carbon. And because of this very unique ability that it can make single, double, and triple bonds, as a matter of fact, all in one chain, it can make single, double, and triple bonds. This can it offers a variety of carbon-based compounds that no other element offers that, and they're very strong bonds. Carbon-carbon bond is very strong bond. It is so strong that I was just reading somewhere that we scientists have found these just one carbon-carbon bond on stars. Okay, and we know that stars have very high temperature. Some of the stars have very, very, very high temperature. So that means that this carbon-carbon bond can even sustain a very, very high temperature. So that these are very unique properties of carbon that makes carbon what it is, and it offers us the different forms of carbon. And we call those different forms of carbon allotropes. So by definition, allotropes are different structural modifications of the same element. They like carbon, not chemically different, but just the way the carbon is arranged. The structural properties of carbon. Like carbon has four bonds, or carbon has double bond, or carbon has a cyclic bonds. These structures, the different structures of carbon, are make the allotropes. That's the definition of allotropes. So carbon can bond itself to at least three different airways, giving us three different materials. We have diamond, the graphite, and the newly invented allotropic forms of carbon are buckyballs, or you call it fullerene or graphene, or nanotubes. So these buckyballs, fullerene, and graphene and nanotubes are the latest additions to allotropic forms of carbon. To begin with, we only knew about two allotropic forms of carbon, and we're pretty familiar of those, diamond and graphite. Uh, let's talk about in detail. The diamond is a very, very strong uh, structure where carbon is bonded to four other carbon atoms, so it's tetrahedral. So the bond chemistry is called four. Okay, because it's bonded to four carbon atoms, forming a giant network of covalent compounds. So they're molecules. Okay, and they're very, very high melting points. It takes thousands of degrees Celsius or 1700 degrees Celsius to change the shape of that diamond. Yes, we can change the shape of the diamond. I mean, we can change the form of diamond into something else. I can turn the diamond into the graphite. But it takes a very high temperature. So diamonds are known to be forever elements, that you cannot do anything to them. But it is not very, very much true. Diamonds are very stable. This is true. But there are two different kinds of stabilities. One is called kinetic stability, and one is called thermodynamic stability. So diamonds are not stable thermodynamically. If I heat it to a very high temperature, I can turn it into a graphite. But yes, at room temperature, it won't do anything. So they are pretty stable in that sense. They are very strong. They are used to make tools, that needs a lot of strength, the cutting tools. So high melting point, as I told you, it takes a lot of temperature, a lot of heat to melt it. Extremely hard. No electrical conductivity because there is no free electrons. So keep that in mind, that uh, the chemistry of conductivity is based on delocalized or free electrons. And there are no double bonds. They're all single bonds. So all of these electrons are very much held by the other nuclei. So there is nothing to move around. So that's why they don't conduct electricity. They're not soluble in most of the solvents. Okay, they're insoluble in polar solvents and non-polar solvents. So it's very hard to dissolve it unless you create certain, circumstances. So they have very strong intermolecular forces, and those intermolecular forces make the diamond what the diamond is. So you have to remember what the diamond is, that it is bonded to four carbon atoms. Okay, so we call it that the bond chemistry is four. The coordination number, as a matter of fact, we call it the coordination number for diamond is 4 because it's coordinated, or it's bonded to four carbon atoms. And they have a tetrahedral shape. So if I have this, and then this one is bonded to another four, and then there is this, and this is bonded to another four. So that's what you're talking about in forms of diamond. So this is one of the allotropic forms of diamond. Here, graphite, where carbon is bonded to three other carbon atoms. So each carbon, as let's say, this is the carbon. Let me make it a different color. So if this is the carbon, it is bonded to 1, 2, and 3 carbon atoms. Now if this is the carbon, it is bonded to 1, 2, and 3 carbon atoms. So the coordination number for graphite is 3. Okay, because each carbon is bonded to three other carbon atoms, and these are very thin sheets of those carbon atoms. They're kind of sliding over each other. So you see there is one sheet is right here, the second sheet is here, and the third one is here. The what you see in between are called London dispersion forces, the LDF, the very weak, the weakest, I should say, weakest intermolecular forces, which are called London dispersion forces, and that makes graphite, a little bit conductor, not really a good conductor, but they kind of slide over each other. So it makes it very liquidy, I should say, uh, uh, or you can say more of a fluid shape thing, you know. And we use it for, hold on one second, there is a word that we use, lubricant. Yes, I couldn't think of lubricant. So it makes it a good lubricant because these sheets can slide over each other, because the the force that is holding them together is the London dispersion force, which we'll talk about later in the class, in the other lecture, which will cover intermolecular forces, that the London dispersion forces are the weakest intermolecular forces. And because of that weakest force, as I'm repeating, that this sheet can slide over this sheet, and keep the same thing goes on. So that makes it a lubricant. So carbon atoms are bonded by trigonal planar orientation. The presence of p orbitals allows a strong van der Waals force that holds the sheets together. Well, it's not really strong, it's a weak intermolecular force. Properties of graphites, they're different from diamond. They conduct electricity because of the delocalized electrons, but it has also a high melting point, and they're also insoluble in water and most other solvents. So these are the two commonly known, or long, known allotropic forms of carbon. Graphite is also the same thing that we use in pencil. So although we call our pencils the lead pencils, but as a chemistry student, you should know that the lead pencil doesn't have a lead in it, that the black thing that you write with is actually the graphite. And graphite is a Latin word, and that means writing. Okay, that's why it was given the name graphite, because this substance could write. So remember that this is coming from a Latin word, means writing. So the pencil that you use has graphite in it. Anyway, as I said, the diamond and graphite were the old or long known allotropic forms. But speaking, since I'm talking about graphite, the other thing I want to talk about, another allotropic form that we want to talk about is called graphene. Graphene is the latest. Graphene is the latest discovered allotropic form of carbon. As a matter of fact, the scientist who discovered it was given the Nobel Prize in 2010. I think it was discovered around 2004. So the thing is that this is the very latest one. In graphene, the sheets that I was showing you here, hold on, the sheets that I was showing you here are like three sheets here, if you pay attention to this. Three sheets of carbon atoms. Uh, Graphene is basically same thing, but each sheet is separate. So if I just cut this one, slip it out, and as I was saying, it's a lubricant. It this kind of slide over each other. So if this sheet slips out, we will call it graphene. Okay, so it is very thin layer of carbon atoms, very thin layer of carbon atoms. And again, carbon is bonded to three different elements. As a matter of fact, in some cases, it's two different elements, so the coordination number could be even two. And graphene is very a good conductor of electricity against diamond and graphite. So as I was saying, diamond and graphite are not very, diamond is completely non-conductor. Graphite is a bit of a conductor. Okay, but graphene is very good conductor of electricity, and it is very thin sheet of carbon atoms that has come from graphite. Okay, and since we have invented graphene, it is being used in a lot of devices, the liquid crystal displays, the LCD screens that we have, the mobile devices, because of the conductivity, all these new latest cell phones that we have, their screen is made of that because it is touchable. You can touch it, you can send responses through this, and it is very flexible and it's very transparent. So since we have discovered this, uh, a lot of industries have made a lot of progress in many different things. So anyway, this is another different form of allotropic form of carbon. Uh, there was another one that was in this invented or discovered, I should not invented, discovered in 1985, another form of carbon, which is called C60. There could be C60 or there could be C70, but most of them are C60. What it means is, let me explain it. Uh, Carbon is bonded to 6 different carbon atoms, which is the multiple of single bonds and double bonds. So it's single bond and double bond. So every other bond is a double bond. So if I keep doing this, I'm going to just do this. Each edge is representing a carbon atom. So if I take this long sheet, and this long sheet, because of the pi bonds, has some flexibility, so I can keep building this. So what happens sometimes, that if I heat it a little bit, okay, this the hexagons, we call them hexagons because each carbon atom is bonded to 6 different carbon atoms, so we call them hexagons. So if I heat it a little bit, it's possible, oh, I'm sorry, it is possible, where did it go? Yeah, there it is. It is possible that some of these hexagons turn into pentagons. So some of the carbon atoms will, let's say this carbon atom will go out, or this carbon atom will go out. So instead of hexagon, it will become a pentagon. So you see there is a pentagon right here. Okay, so it is possible that if I skip this carbon atom out, then this carbon and this carbon will bond and it will make a pentagon. So if I have hexagons and then those hexagons are connected by the pentagons, that give us a very unique compound called fullerene. Okay, in which I can have 60 carbon atoms bonded together, and most of the 60 carbon atoms are going to be hexagons except 12 pentagons. Okay. um, Let me see where it is. So I'm introducing fullerene here. Fullerene is another allotropic form of carbon that was introduced in 1985. Of course, the scientists were given the Nobel Prize in, I guess, 1990 something, 1995, I guess, and they were researching in Rice University when they found this. We also call them buckyballs. Okay, they look like a regular baseball. If you actually not the baseball, the soccer ball. If you actually look at the soccer ball, um, as a matter of fact, if you have a soccer ball at home, I want you to go home and take a look at it. That soccer ball has some pentagons, okay, separated by the hexagons. So every few hexagons, you know, will have a pentagon. And if I take this sheet and I kind of turn this around, into a ball shape, it will give me a fullerene. And it is 60 carbon atoms in it. And instead of making it around like a soccer ball, if I turn this into a long tube, I call it a nanotube. So depends how they're shaped. But so if you pay attention to this one even, you see that this is a hexagon right here. So I have those hexagons, okay, which are kind of thin hexagons. They are kind of turned into a long tube, and here is the ball shape, and it's called fullerene. So this is a nanotube, and this is a fullerene. They are separated by the double bonds and single bonds, and here it is also separated by the double bonds and single bonds. They have very interesting properties. They're super strong. They conduct electricity, and they're very good conductors, and they have a lot of industrial uses. So again, another form of buckyballs or fullerenes. Again, you see you have, this is, what is it, 1 2 3 4 5, this is a pentagon, okay, and you see that the pentagon is bonded to a hexagon. Okay, so if I take these hexagons and just turn them into a ball, take this whole long sheet and turn this into a ball. So carbon atoms bonded in the units of 60 atoms, forming a structure similar to the soccer ball with interlocking six-sided and five-sided rings, the pentagons and the hexagons I'm talking about. The extra p orbitals, the double bonds, make it a very good conductor. The strong covalent bonds, and so it's a very strong material, and it is insoluble. They are soluble in some non-polar solvents. Some, not very easily, but there are some non-polar solvents that you can dissolve it in. But overall, it is insoluble. So these were the allotropic forms of carbon. We talked about graphite, we talked about diamond, graphene, and fullerene. The very last one is silicon dioxide. It's also called quartz. You have probably heard of watches as well, because they have very shiny surface, and so they are quite commonly used in to make watches. So it has silicon in it. It creates a giant covalent network structure of silicon and oxygen, silicon dioxide, and that results, 1 to 2 ratio. And it is also the same chemistry, that each silicon is bonded to two oxygen atoms. So those linear silicon. If this is silicon and this is oxygen, then this is silicon and these. So these are the kind of linear shaped compounds, and they are bonded together in a way that it makes a very strong compound. So you can find all this in your book in quite a detail. I will suggest everybody to read this, because I, of course, cannot cover the whole thing. So it is from page 117 to 120, I should say. And a lot of questions will come out of these allotropic forms of carbon. So you should know all allotropic forms of carbon and quartz. So that, according to the pacing guide, this is what we were supposed to learn today. As I'm not in the class, so your job is to make sure you take notes and complete all the practice worksheets in the packet that cover this material. So thank you very much, everybody, for this attention. I appreciate it, and all the best. I'll see you on Wednesday.